Juan, can you hear us online?
Current chair of the national group of IAPSI. And there we go. So IAPSI is the International Association for Bridge and Structural Engineering. Is based. Can you hear me now? Can you hear me better? Okay. So IAPSI is the International Association for Bridge and Structural Engineering, and it's based. The mission is to exchange knowledge and advance the practice of structural engineering worldwide. And so that covers all aspects of engineering, of structural engineering, all types of structures, all types of structural materials, not just concrete, not just steel, and all aspects of the construction process. So we have about 2,500 members worldwide, and which is relatively small. It's considered an ASE here in New York is over 3,000 members, so it's a small group, but it's a very interesting group because you get to meet people who are working at a very high profile project, and that's very interesting. Did I skip one? Okay, what do? We organize conferences and webinars worldwide, and each national group also organizes webinars that may be just online, or could be both a hybrid, like we're doing today, where we have a group at a specific location. My challenge as the chair of the US is that it's a very big country, with very spread out. So when we try to have multiple events simultaneously in different cities, so that there are more opportunities for networking, and more people have access to the benefits of being an IAPSI member. But of course, our events are open to members and non-members. An additional thing here in the US that we can provide PDH for those who need it. If you're a member, you get your PDH free when you attend the meeting. If you're not a member, you can opt to get a PDH and pay a small fee. So, and to that, I'm going to add that we have this form that you fill out if you want PDHs, if you need them for your certification. And so if you can circulate that, that's great. And for those who are online, as long as you stay logged in until the end, you will get your certificate if you register for that. All right, our next Congress is in Korea. So in South Korea, so I hope few people will take this opportunity not only to listen to interesting presentations, but also to get to know a faraway country. I'm certainly looking forward to being there. And unfortunately, the call for abstracts closed this month, so too late for that. But certainly attending is.
Did it reopen? Did it reopen today?
I think they extended
Oh, they extended
the deadline. Yes.
Okay. Well, there you go. If you want to send an abstract, you still have a few days. One interesting aspect of actually is that we have these commissions that deal with technical aspects of engineering, and the task groups. Task groups are more committees that have a special purpose, whether it's to publish a book or prepare sessions for conferences or write papers or special issues of the journal. And we're going to have a very interesting event in November, November 18th, to talk about the task groups, what they do, and specifically 4 or 5 different task groups that have several members in the US and are open to taking more members. In some are open to taking more members, and it should be very interesting. Okay, so these are the publications, the journal, which is a very well-known journal, very cited for those who write mostly in academia. They really need to publish, so it's a well-cited journal. And then the special publications, like you see the Coral Bridge collapse, that was an interesting one, and other publications that we more with. It's like, for example, they have with one on design with glass, right? So, and then of course the Congress proceedings. We also have a very strong Young Engineers Committee, and raise your hand if you're in the Young Engineers Committee. I think we have a couple, right? Rudy here. No? Oh, okay. Well, Sebastian, of course, is the chair globally, but he's in Canada today, so he's going to be here. And the benefits of the student membership is that you get very discounted membership and access to the journal and discounts at the conferences. As I said, Sebastian Mahut is the chair globally, and Riley Coverage in California is the young member representative to the board of the U.S. National Group. And he's done an excellent job at organizing events. We had a photo scavenger hunt in the summer, and we're very membership program next year. So these are the board of director members. It's great to have that wide support from professors and people in consulting. So reach out to us if you are interested in active in the association. In 2024, 2025, mostly hybrid seminars. As I said, the photo hunt, that was fun. The task group webinar is coming up on November 18th. And we publish a newsletter, which should be periodical, but every 3 or 4 months. And with that, I'll leave you with that. And then I think you can all read on the screen his qualifications. I'm very pleased that he's presenting for us today.
Yeah, thank you, Maria. This is a bit of a technological crossover. I feel like it's a TED talk or something. And you switch the slides. Important. Okay, maybe we should get rid of some of these extra people who we have to come in. Okay. Thank you.
We still have this meeting, I think. The final piece of that, remember, was new for it's like the one.
Top left. No, I think that one.
Okay, now,
No, okay.
Hello, and thank you, Maria, for the invite to speak today. I'm going to talk about the engineering for a circular economy. And before I get into the good stuff, as Maria said, this is a PDH.
Recording in progress.
PDH course, so I need to show you the boring stuff as well.
Too many computers.
So this is accredited. And the goal of this presentation is to inspire engineers to think about beyond the linear economy into a circular economy. And the idea is to introduce what a circular economy is and then go through 5 case studies, which each had a different aspect of the circular economy in their design. So we need to identify the principles of circular economy. We want to recognize the opportunities for extending the utility of elements beyond their typical life. We want to understand the differences in the design of using reclaimed or reused materials instead of new ones, and we want to understand adapting time processes.
Excuse me, I don't know if you can hear me, but the audio online is not very good.
Hear you for sure.
Were you able to hear me better, or was the same?
I could hear your introduction fine, Maria, but I'm having a hard time now that the presentation is on.
Yeah, it's not coming through here either.
I think that's going to be worse. But
You think so?
Wait, if you hold the mic like I was.
the problem is I
not-
need 2 hands to operate 2
Okay.
different computers.
That sounds fine as you are now. I don't know.
Let me try putting it back on my head. Maybe the mic is the wrong way. How's that? Is that okay?
That's good.
Thank you, maybe.
Yeah, keep holding.
I think what we don't need is like a third piece of technology. Okay, so this is what you're learning. This is what you're learning today. So let me start by introducing what I mean when I talk about a circular economy. So on this slide we have 4 different routes from left to right. Let's start with a linear economy. This is highlighted in red, and this is maybe the type of construction economy that we're familiar with from the last 50, 75 years or so, where we extract materials from nature, we refine them, we produce construction materials, we fabricate them, and we assemble them into structures. And then we enjoy that structure, we use it for, depending on the typology, anywhere between sort of 20 and 70 years. And then it's the end of life of that structure, we demolish it and we throw it in the bin. So this is our linear economy baseline that we're familiar with for sort of the last 75 years or so. The goal of a circular economy or anything better than a linear economy is to reduce the number of those black boxes that we're going. So each one of these black boxes has energy and emissions associated with it. So when you extract material, that causes damage to the environment, it releases carbon dioxide emissions. When you refine, produce, fabricate, each of those steps involves carbon dioxide emissions and damage to the environment. So the goal is to reduce how many of these steps we need to go through by minimizing minimizing the process, keeping it in smaller and smaller loops. So compared to a linear economy, a large loop economy is an improvement. This is something where we're looking at recycling. So if you think of our steel industry, when we demolish the structure, instead of putting it in landfill, we say this has value to us. We want to shred it, prepare it, melt it, and reuse it again in new structures. This is our large loop recycling economy. This is better than a linear economy. We're not extracting more ore from the ground, but we still have to melt stuff at thousands of degrees and go through all of the carbon-intensive processes again. What we're looking for when I talk about circular economy today is that blue loop. So instead of demolishing a structure, we're looking to deconstruct it. And when you do that, you can maintain the value of the elements themselves and recondition them instead of shred them and melt them. And then we can do some refabrication, but we don't need to extract, refine, produce the materials from scratch again. So we avoid a lot of the really energy-intensive boxes. The smallest, tightest loop, the maintenance economy, this is maybe our goal. This is when instead of a structure having an end of life, we just keep using it. So adaptive reuse of buildings, maintenance and upgrading of existing infrastructure. This is the best way to avoid emissions and damage to the environment by maintaining the use of what we already have. this is not about the circular economy. This is sort of a more general net zero design guide that the iStruct team produced a few years ago. And this goes beyond economy to other things that we can do in our structural design. What I want to point out here is how these two things interact. So the general guidance is that we should use less stuff, we should specify low impact material, and we should then, if we're really in trouble, figure out how we can offset our damage. Now, those first steps, the build nothing and the build less steps, these are the maintenance economy. This is keep using what you already have. This is kind of our first port of call. This maximizes the use of our structures. Build clever, build efficiently, and minimize waste. This starts to interact with the circular economy a bit more. So can we use existing materials? Can we design structures which use elements that we already have? Can we efficiently adapt different structures, different elements to match a new system? This requires a change in thinking, but it allows us to work within the hierarchy that we have. The large loop economy and the linear economy, these really fit into this tiny little slice. So the bigger the area of these sort of wedges, the more impact you can have on the design. So those bigger steps, the maintenance economy, the circular economy, this is where you have the biggest impact to avoid emissions. When we get down to specifying good materials, this is obviously important, but we may be already using 1,000 cubic yards of concrete. At that point, we can say, okay, let's use low carbon concrete. So this works within the large loop and the linear economy. We're still potentially using new materials, but we're just trying to specify new ones better. So what I want to talk about today in these case studies is these three stages of the circular economy. So I want to talk about deconstruction. So at the end of life, how do we deconstruct the bridges or the buildings that we're working with instead of demolishing them? I'll talk about the Montreal Olympic Stadium there. I want to give 3 examples of designing with reuse for wood, for masonry, and for steel. And I'll talk about designing for disassembly. So thinking about how when we build a structure from new materials, how can we facilitate future engineers in taking that apart and maximizing the benefits of the circular economy there. And these 5 projects are from different continents and from contributions from different offices from SPP. And we have, so we'll start in North America with the Montreal Olympic Stadium. That's a deconstruction project. Then move to Europe and back to North America for some material reuse, and then finish in Qatar for Stadium 97. So Montreal. This is a collaboration between the New York office of SPP and Stuttgart and Bergen offices. And what we're looking at for this project is how to maximize the existing life of the Montreal Olympic Stadium, which has a bit of a history. So it was built for the '76 Olympics, which were a great Olympics. But you might notice there's a crane in the background because the stadium wasn't quite finished at this point. So the pole was done, but the tower that was going to support a new roof wasn't completed until a decade later. So in 1987, they finished the tower and installed this really ambitious roof, which is supported by these cable stays in the tower and sort of expands into the tower like a squid. This was very cool, but it, as you may have imagined, could have some maintenance issues, and was replaced in the 90s by a new roof. So this roof is still supported from the same boundary conditions from the top of the tower, but this one doesn't move. This is static, and this roof also had some issues. So it had some damage and deterioration, and snow loads in certain conditions was a problem, and this limited the use of the stadium. So the client said, "We'll keep the stadium, but we'll build a new roof again." So this would be the 3rd roof. So this is good news. The client is following a maintenance economy. They're keeping the stadium, and they needed to replace the roof. And the opportunity here was to say, in 2021, could we look at deconstructing that roof and reusing it for other things? Could we get additional life out of the structural elements in there, and go away from that linear economy approach? So first stage was to figure out what the reuse scope was, to define that we have all the roof elements coming out, and then to say what is in that roof. What are the details? So we looked through archive drawings and structural models, and made sort of a high level but fairly detailed distribution of all of the element types and quantities and typical lengths that we have. So this is essentially a tensegrity roof with a membrane on top. So lots of structural steel cables and really large pipe struts, sort of 60-foot diameter, 60-foot length and 3-foot diameter. These are really big elements, not typical for a lot of the structures that we might consider for deconstruction. So we started with this idea of what was potentially available in the roof to come down. And then we had to say, well, if we had this supply, what demand could we generate to use these elements? And the goal was essentially to work down like a sports bracket and to say, well, what supply do we have? What demand do we have? What can we build in the middle? It's a shame that this isn't the baseball bracket. So the next stage was to generate the demand. So there were 3 routes that we took to generate demand for reusing these materials. One was to run an internal competition at SPP for design ideas using this specific material inventory. So you have these cables and membrane and struts. What designs could you produce? And so we had a first round of sort of 25 entries, and then narrowed that down to four finalists who went through concept design and produced some reports and structural calculations. Some of the team that worked on that are in the room here today, and that was a really interesting project for us to see what can we do with the material reuse. The owner, the client of the stadium, also ran an international design competition, had something like 50 entries, and narrowed that down to a short list of 10 winners. And then the third group was that they spoke to engineers and architects and construction professionals in the city of Montreal and said, could you replace any of the structural elements on your buildings at the moment with some of these elements that we have here? So they had a sort of productive workshop in real life. If we look at the 4 SPP designs for a minute, we had sort of a range of different structural typologies and these 4 different approaches. And part of what was useful about this was we could match the typical elements that we saw demand for these 4 projects. So some of these elements no one was using in their proposals, and some of these elements were in quite high demand for some of the proposals. So this gave us a steer on what we should guide the client to ask to be deconstructed and safe for reuse. So we didn't think that there was much use for the line and membrane or the flying forks in the roof, but we saw a lot of opportunity for the stay cables. So this gave us a steer and told us to say to the client, how about you save 20% of these elements, 80% of these elements, 100% of these ones. Some materials weren't suitable for reuse structurally, so the membrane was deemed to be better used for non-structural uses like bags, or some of the elements were maybe better to be recycled because of their unusual shape. Made them really hard to reuse in an essential way. This gave us a targeted inventory, the supply, and a narrowed down demand. And then the contractor was asked to follow this through. And this was a really interesting process because we could see how deconstruction works in real life, a real project, and understand some of the challenges. So one of the challenges was that the logistics on site were limited. The contractor maybe hadn't thought about deconstruction earlier enough in their planning, because the conversation hadn't come up early enough in the whole project. And this meant that they had really large cross sections that they couldn't move easily with the crane into their element site. So, well, we might want to keep a piece of 45 feet. The contractor said we can't lift it unless it's cut down to 15 feet. This is too heavy. So that already limited some of our reusability of elements because of the site logistics. For some of the structural cables, the way that they were being removed was maybe not ideal for maintaining the value of the elements. So you see here quite a tight kink radius in this stay cable that was removed down. With a little bit more planning in this process, they could have maybe supported it more evenly and avoided that tight radius. But this is going to cause some damage to the cable as it's removed. The deconstruction is different to demolition, and some of the contractors on site were on board with the variations that we needed, and some of them were less well informed. So when they were cutting some of these cables, you want to stop them unraveling. So the process was either to apply a tight a tight wire around it to stop the strands spreading. Or in some really good situations, we could reuse the existing clamps from the membrane system for the cables, like on the left. So this is really holding the integrity of that cable section that remains. On the right is how some of it ended up, where there was no care to stop it unraveling, and this is now not a useful cable for us to reuse after deconstruction. Some other things that came up was the information that we had didn't include on-site chemical tests for some of the paint. So while most of the roof was the 1999 roof, which didn't have lead paint in it, some of the elements were from the 76/87 roof, which did have some lead in it, which meant that some of these elements were contaminated, and the contractor hadn't accounted for fixing that on site or at all. So these were recycled instead of reused. Some of the elements have coatings which are in good condition, and some of the coatings are damaged and need to be replaced. So the deconstruction would need to, the reuse of these after deconstruction would need to account for the fact that coatings could be damaged in that process and would be fixed later. Another issue that they had on site was storage. So once the elements come down, you need to move them out of the way quite quickly. And if the storage solution hasn't been arranged, or there isn't an end of use for that, then the storage space can be a limiting factor. So there were some laydown areas around the stadium which they could use for elements, but a lot of the really large struts that were removed had to be recycled because they didn't know where to put them, and they couldn't keep them on the site. So some quite high value elements ended up being removed because of logistical challenges, instead of maybe other challenges like the lack of desire to use them. Transportation was the final sort of issue that we dealt with, where some of these stay cables were, sort of 4.5-inch diameter. These are really big, and to get the value out of these, you need to keep them in their initial length, hundreds of feet. If the deconstructor isn't ready and skilled in spooling cables back on the drum, then for them to transport them off site, they're going to cut them down to 50-foot lengths, and this loses some of the value for your cables. So that final stage of getting everyone on board in terms of spooling the cables and maintaining the value is a pretty key and important part. So where did this leave us? This left us with less supply than we initially anticipated. So some elements were smaller, some we didn't get at all. It left us with our narrowed down selection of designs. And then the client proposed maybe only a few of those to take forward. And this is kind of where we are today. There are some non-structural reuses of the deconstruction material going ahead. We're hopeful that we can realize one of the structural or partially structural reuses for some of this material. But we'll, hopefully I can update on that in a year or two when we've gone through that process. So this was a project which is about deconstruction primarily, and for elements which are not typically deconstruction, I think we learned a lot on how that can change and what we could do next time on a project to make sure that the deconstruction is a little bit more successful. But I think what's important to say is the client and the contractor, within the bounds of what was set up for their contract, worked really quite well on this, and there's a willingness and an opportunity to do things and learn, as long as everyone is set up early enough on the project. Okay, so goodbye deconstruction. Let's start talking about reusing existing materials for design. And this is a project which was completed for as part of the enabling works for the Paris Olympics last year, and I guess also has a little bit of deconstruction in it as well. The brief for this project was that the client needed a bridge across the Canal Saint-Denis near to the Olympic Stadium, the main Olympic Stadium site north of Paris. They needed a bridge there, which was accessible and permanently functioning. So they had sort of a tricky situation where they already had two bridges on the site, but one of them was a movable bridge that didn't move, and the other one was a footbridge which was stairs only and quite steep. And you can see a nice footbridge, but this didn't meet. This meant that there was no wheeled access from one side to the other without quite a large detour around the canal. So the brief was to replace this with a connection, which was sort of 5 meters wide footbridge that would go across the canal up at a certain height so that you could still navigate the water. So this was the initial client brief and the first design. What was exciting here was that the client already owned some of the structures on the site, and were quite keen to, the context of this is sort of 2020, 2022. They were quite keen to ensure the supply time, the logistics, and also the cost of steel. And that in 2022, there was a lot of fluctuation in supply and steel costs based on sort of the geopolitics at the time. So the team proposed to reuse the existing movable bridge, make some condition assessments and amendments to it, to use that as the primary crossing for a bridge of this site. So what you see on the right is the reusable, the movable bridge as it was, and on the left is the rendering of how this would look instead. So you have you go from a 5 meter to a 13 meter wide footbridge with a similar ramp configuration, but you're reusing the existing bridge and bridge materials to achieve that crossing. So the ramps were new, but the main steel deck was based on the previous one in a different configuration with different boundary conditions and supports, and there was some pile reuse as well. So this was a challenge for the team in terms of how can we go through the reuse process here and justify the reuse of this bridge in a different configuration. So the good news was that the client, the bridge is not so old. It was built just around 2000, so the client had good documentation, and the materials were not built essentially to modern standards. So in addition to the existing documentation, the team requested some condition assessment surveys and spot checks to look at well details, corrosion, and to identify which areas would need some maintenance and which were sufficient. And then using this information, they went through and proposed what fabrication amendments would need to be made to this bridge to make it fit within the new scheme. So what sections would need to be removed, shown in orange, what sections would need to be added, shown in blue, to get this to fit within the new scheme. The main change that had to be considered was the fact that the movable bridge was supported variably at 3 different locations, and the new bridge was supported at 2 static locations. So while the bridge is the same length, the span is different and the support conditions are different. And that meant that the shape of the bridge was kind of wrong, because the existing bridge was fabricated for a different configuration to deal with deflection. And if you change your supports, you get additional deflection over the canal, which was a problem. So one of the changes in design was to consider the actual geometry of your structure and how that's been designed previously, and to adapt that with your tolerances and your clearances over the canal so that you can successfully reuse that steel. So this was, I think, something which didn't seem obvious at the time. You consider that you have a deflection limit. You don't consider the initial change in geometry. Other things that needed to be done was assessing the concrete quality of the foundations, and deciding whether there was the depth of carbonation that had gone through, the existing strength, and whether that met the durability classes that they would need currently. So this allowed for with some additional work and study, and allowed for the foundations to be feasibly reused, even though they didn't actually meet the requirements of the modern Eurocode. So the main change here was to do the fabrication work on that steel deck in situ, to do the condition assessment where it was on the site without transporting the bridge away to a shop. So they built a temporary shed and workshop on the site. And then once the fabrication and repainting was done, lifted the bridge on the canal and rotated it into place to drop into its new position. So this, I think, was a really nice example of minimizing transport emissions, minimizing new material use emissions, and tying that in with a schedule which was more controllable. They already had the steel on site, and costs which were a little more controllable. You already own the steel. You didn't need to buy new steel at current market rates, which were really changing a lot. So what was one of the nice things that we did after this project is we went back and said, how good was it to reuse the bridge? What was the embodied carbon impact that we could estimate using the 13-meter bridge instead of a 5-meter bridge, and understand what some of the design options and changes were. So the overall headline was that the main crossing had a significant reduction based on reusing that steel deck. So what you see in the middle of the chart is the the initial design that was worked up, so the new narrow 5-meter bridge. And then on the right, you see the reused wider 13-meter bridge. So these are total carbon tonnages. On the left is kind of a fictional example of if you built a 13-meter bridge from new at the time. So the one on the left was never really considered. The benefit we see is between the middle and the right. So what you see is that the main crossing steel really reduced. And what you also see is that the steel for the ramps and the stairs and approaches is a really significant portion of the bridge now. So while there were some savings on the main crossing, we still had to use new steel from a linear economy process or a large loop economy process for the ramps and approaches. And that's a significant portion of a structure like this. So you can do really well on that main crossing and then have significant impact from the rest of it. We think just for that main footbridge, there were some comparison options that the team considered quite early on, and hard to remember to do two at once. And you saw a real benefit for the main footbridge. These are from the early concept comparisons that they did at the time. So check whether you had steel only or a steel concrete, or a sort of combination of overhanging caissons and a main console. These compared to that larger reused bridge, you're seeing that significant benefit. So reuse is good. The main crossing, it's harder to deal with when you also have other stuff going on in your site, which dilutes the benefit. We also had the opportunity to track how these calculations developed throughout the design stages. So from schematic design to developed design to construction documents, the changes in design partially to deal with the reuse of steel, but also partially to deal with better estimating and decisions that the contractor made on how they were going to fabricate things, meant that the overall emissions went up, around 15% from schematic to construction documents. And this is something that we've seen a few times in some of our bridge projects, is that there's sort of a carbon creep that comes in when you complete your project, which is, I think, important to consider quite early. So, this is not circular economy dependent. This is a general embodied carbon comment, but interesting to note here. Okay, a second designing with reuse.
What happened to the other bridge?
The other bridge is still there. The initial brief was to get rid of, to remove it, but it has architectural significance. So I think at the moment they have two bridges parallel to each other, one which is accessible and one which is not. There was a thought to deconstruct that and reuse the elements for another structure in the area. But I think that's, the Olympics is done, and that was the main driver for this stuff. And at the moment, I think the municipality have other things to think about. Good question. Okay, so let's change tack a little bit and move to Stuttgart in Germany. And this is a project from SPV's Stuttgart team who've done something I think really interesting with material use beyond what we typically think about for a lot of our structures. So it starts with a sad story, which is in 2021 there was a fire in the bus depot in Geisberg in Stuttgart, and this was this damaged a lot of buses and damaged the bus depot. And the brief from the client was, we need a new bus depot that won't, if there's a fire in it, we won't lose everything. So the brief had this, the initial design brief had this system which had these fireproof walls which separate the structure into separate lanes, and open-ended structures which allowed for better ventilation to stop heat and smoke gathering in there. So this was the initial brief, and most of the project is about achieving this nice sort of glue lamp curved roof structure with these boundary firewalls. This is what it achieved. So this is the rendering, and this is what it looks like now. Pretty good effort. A major part of this challenge was to think about how to do the fireproofing between those walls. And they were looking for somewhere where cost and sustainability and fire resistance and appearance would meet together, which is always a hard challenge. And the team looked at a whole bunch of options. So whether they were concrete solutions or wood solutions, masonry solutions, or other materials that they could work with. And they ended up with a proposal to use recycled bricks to form these walls. So these are firewall partition walls which have codified wind load requirements and have to meet fire requirements. So these are partially structural elements, even though they're not the primary structure of the system. So after the team proposed recycled bricks, it was the question of saying, how do we execute this on the project? What do we need to do differently? And what I think is so nice about this case study is they didn't need to do so much differently at all. They just wrote recycled brick on the drawings. So it looks like brick, but it says recycled brick. They in the project specifications, they said recycled brick, and they gave an example procurement. So you could get recycled brick from somewhere like this. And this wasn't a fancy supply chain. This was example they gave was essentially an online marketplace for reused material. They said you can buy these bricks here; they should be sufficient. In the end, they ended up working with a supplier who specialized in reclaimed bricks for structures and sort of developments. And Wienerberger, who were doing this work, were able to provide a little bit more information. So they went through and did some structural testing, so compression testing on the bricks to meet certain requirements, and they did some fire testing. And this gave the team confidence that these would meet the structural and fireproofing requirements that they needed. Reclaimed bricks have a few nuances. So first they wanted to see how it looked, and then they had to deal with the mortar. The mortar that they were going to use a little bit differently. So with the reclaimed bricks, I think there's an understanding that the mortar should be a little bit thicker to deal with some of the tolerances for the bricks. So the mortar is a little bit more visible in some of these prototypes. So what you see here on the left is three mortar options for the same type of recycled brick. And then once they did the mock-up, they then chose one to install on site. You have these masonry infill panels that they're installed as they go. So what was useful here was establishing this contact quite early with the client and the contractor, and making it something which could easily be procured and tested without being something with onerous technical requirements. I think this is a really successful example of not changing the whole project design, but just changing part of your procurement route and client conversation quite early on to give you significant saving on bricks. We think of the humble brick as a really normal structural material, but they're made of clay, which we dig out of the ground, and then we have to fire them. So anything which requires heat uses all that energy. So fired bricks are not really low carbon materials. They're common materials, but they're not low carbon. So if you can reuse them, you have significant savings. Okay, and then let's move to the last designing with reuse project I want to talk about, which is back in New York State. And this is a project called Circulating Matters that we did in the New York office in partnership with the Circular Construction Lab at Cornell University, where we have an ongoing research partnership. And this is a project which, similar to the Lucy Bergsagel footbridge in Saint Denis, hides the deconstruction stage of this project towards the design reuse in quite an interesting way. So the project started with a part of Ithaca, New York, called College Town, where the developer had 13 buildings like this you see in the foreground, which were destined to be demolished and replaced with sort of 6-story high density student housing. And typically what that would look like is demolition. You get an excavator and you can take one of those buildings down in 1 or 2 days and turn it into a big pile of sticks. And the value of this pile of sticks is essentially zero. You can't use any of this stuff again. It's all been damaged and broken and nicked. And for one of these 13 buildings, the client who owned one of these 11 buildings, the client who is based in Ithaca, suggested to the university that maybe they could work together on doing something a bit smarter. And this allowed for the deconstruction of one of the portfolio. So this panelized deconstruction involves making some clear cuts and removing parts of the structure in large sections, and then taking that apart on the ground, maintaining the value of the elements in there. It also involves stripping out a lot of the finishes and non-structural parts inside, which have architectural reuse value too. So with this deconstruction project, the Circular Construction Lab did an interesting economic study of sort of a head-to-head comparison of one of the demolition projects and one of the deconstruction projects as part of this portfolio. And there were some, I think, slightly surprising outcomes from the study for these two buildings head-to-head, which was some of them are not surprising. It's much faster to demolish a building than to deconstruct it. So that's sort of the third pair of columns from the right. If you demolish a building, it's 10 labor hours, or in tens of hours. And then if you deconstruct it, there's a lot of work that goes on in taking it apart, taking the elements apart, getting the value out. So the labor cost and labor time is really high for deconstruction. What they found is that the cost was the cost. There was a revenue from the deconstruction compared to the demolition because you had all these materials that were then sold. So you spend the time to deconstruct it, and then you sell the materials to people who see value in it. So instead of paying for tipping fees, you sell it to people and get money back for that process. So that's essentially the trade-off. Do you take more time to extract the value and sell it to other people, or do you take less time and lose the value and pay someone to take it off your hands? There were also some carbon emission differences. So the main one is that there's less heavy equipment used in deconstruction, a lot more people doing it, and we breathe less carbon dioxide than an excavator uses diesel. So that's the other head-to-head sort of clear difference. What that left at the end of the deconstruction project is a stack of wood, which needs to be processed and sorted. And this is a time-consuming task at the moment. There's research on how to streamline this, and some exciting startups in the Bay Area in California on how to automate a lot of these processes. But essentially, you're moving material around and you're manually denailing it and assessing whether there's significant damage or not. This is a deconstruction of these projects, and where the design for reuse came in was that we partnered to design a small installation on the Cornell campus of a staircase. But as a habitable staircase, it required a City of Ithaca building permit and a stamped engineering letter and structural report. So we had the opportunity to go through some mechanical or material assessment to give design values for the wood that came out of this project. So we basically looked at three different ways for assessing the design values. And we also recorded how the design changed over time. So I guess for an engineering audience, the schematic design did not involve engineering input, and detailed design and construction design did. So we looked at how our design for deconstruction with reused material varied, and how we could assess the design values. The main design difference for reusing materials was to allow for some flexibility in the length of these sections. So we had a good idea of what material lengths we had and the inventory that was available, so we could design appropriately for it, but we weren't quite sure. So the design solution here dealt with the ability to slide members past each other, to have face connections, which use the cross-sectional geometry and allow for some change in length over time. So this was sort of the key design change from an architectural perspective. And from an engineering perspective, what we cared about was how to get the wood design values, or how to feel confidence in the wood design values that we used. So we went through a flowchart process of 3 different options, trying to do this through species identification and sort of an initial visual grading of what this looked like, through understanding the specific gravity of the material that we had, and through destructive testing to check the modulus of rupture and modulus of the elasticity of the samples. Species identification was harder than we would have thought, and we went to 2 different specialists who had some disagreements, and these disagreements could have a really significant impact. If you assume you have a high quality species like southern yellow pine, or any of the hard pines, that's going to give you values which are significantly higher than eastern white pine or some of the less strong northeastern softwoods. So that species identification was quite important. And if you assume the worst, you lose a lot of utility of your material. If you make an assessment and it's poorly informed, then you have a seriously unconservative design. So species ID was promising, but hard. You have to send samples to the specialists, and they don't always know. The other method we used is we took some samples and cut them into defined sizes and moisture controlled them, and then measured the specific gravity. The approach here was to use the density of the wood to use formulas which correlated density of the wood to modulus of rupture, modulus of elasticity. And this gave us a way of estimating design values for the wood to be reused. And then the final step was we used those samples and did some destructive testing, and from our small population measured some modulus of rupture and modulus of elasticity values for sort of a lower bound and average. And this gave us a range of different values. The construction design assumed that we used for this assumed the worst. It assumed the worst species for the two groups of wood that we found. And what that meant was that the design was sufficient, but we were losing a lot of value compared to some of the other methods that we saw for group one. So group one was some sort of hard pine. And if we use the NDS values, that would give us certain sort of, say, 50% increase compared on the lower species values. If we use our destructive testing, we actually found that the modulus of rupture on those small samples higher still. And then if we use the formulas from the forest products lab, which correlate specific gravity to these mechanical properties, we've got even higher values still. So not to suggest that the formula approach is the correct one with the current, for reclaimed wood, or the current approach they have, but there seem like opportunities to use some of these methods to give us more confidence of the design values of reclaimed wood, which would give us better utility of it than simply just assuming the worst and not knowing any more from that. So in the end, we had a nice installation on campus, and this was there for 6 months. And then in a true circular economy approach, it was then deconstructed and reassembled at our OMI in the Hudson Valley. And this is still there now as in a slightly different configuration, but essentially using the same design logic to put this together and to continue getting value out of that material. If you go to our OMI, you have to go quite far in to find it. It's in sort of the architectural graveyard right at the top. Okay, we're doing last project, and then we can have a rest and ask some questions. So the last project I want to talk about is Stadium 974, and this is a design for disassembly project, and completed by the Stuttgart team of SVP. And this was a stadium built for the FIFA World Cup in 2022. And some important context for the FIFA World Cup in 2022 was that it was in Qatar, which is a country of 3 million. Thank you. And the population that arrived at the World Cup was 1.4 million. So the population increased this temporary event significantly. And while there was a demand for these 8 stadia for the World Cup, there was an understanding from the organisers that they didn't need all of these stadia forever. You know, some of these could be removed. So Stadium 974 was designed to be disassembled because the land that it was built on has value and wanted to be reused for other things. So the principle was, how do we build a stadium that we could, a 40,000 seater stadium that we could use for 4 weeks, for 6 weeks, for a few more events before and after, and then remove it and use that land. Land has value to us too, and reuse the stadium in some configuration somewhere else. So the logic was that this is a modular stadium which can be disassembled and either reassembled as a 40,000 seater stadium or as smaller sports facilities which have some different value configurations. So a really interesting challenge to work with. And the design team took an approach which is based on the idea of sort of a high bay warehouse, where you have this very regular racking system. And these warehouses are usually racks to store sort of palletized material. And these can be built in all sorts of configurations in different parts of the world. And the challenge here was to do this, follow the same logic, but to do it with shipping containers as the unit instead of pallets. And to use these containers as the primary program, the primary way of viewing the stadium, and also the way of transporting the material to different locations. So in the end, the stadium looked something like this, really large, regular frame with shipping containers that plugged in to form the different functions of the stadium that you need. And they formed sort of 2 functions. So some of them had all of the mechanical services stored in them. So these were sort of prefabricated and then would need to be plugged connected together, but all of the services were encapsulated in that container. And then all the materials and the structure of the stadium was designed to be cut to length to fit within containers for transportation to the site from where it was fabricated and then to its next location as well. Columns had splices at locations which would allow it to fit in the container. You see some nice clean renders of the raker seats stacked and folded in there as well. So this is the idea that you think not only about the process of fabrication design, but also about transportation, disassembly, and relocation afterwards. A really helpful part of this is to have a clear, repetitive structural design. Now, this is the sort of stadium cross-section which I think you can only dream of for most projects. Really clear load path, really clear stability system. This is the sort of thing that you can execute with architects if everyone's on board. The whole project is really clearly well aligned on designing for deconstruction, designing for disassembly and modularity. So if everyone's on board, you can prioritize the important things for that, which is repetition, simplicity, control of a regular grid. So this is a really key part of how this works, is an understanding that the defining goal is to have something which is rational, modular, and can be understood and organized. Another part of the system which is really important is the idea of reversible connection for design for this assembly. So how can we prefabricate this somewhere else, assemble it neatly, and then disassemble it as well? So the idea of using sort of these single pin connections helps avoid some of the issues you have with multiple bolted connections seizing over time, being hard to remove. But it helps also with the load path during assembly and disassembly as well. So this is the logic is that all of these connections are visible and accessible and can be mechanically efficient to be removed. Another key part of designing for disassembly is rationalizing your structure so that if you were to reconfigure your stadium into another life, you have a kit of parts which is sort of functional and interconnected and can be readjusted. So this column beam detail is a really good example of how that logic comes together. You have a standardized column size with these shoes that pick up the beams on the grid. And within those shoes, you have sort of 3 different widths of beam, which fit within the shoe, which fit around the shoe and extend past the shoe. So you have sort of 3 different dimensions, 300, 400, 500 millimeters, and then you have these 3 different thicknesses that you can work with. And that gives you 8 different structural shapes to work with for your design to meet the different demands for different parts of the stadium. So this connection, I think, tells a bit of a story. This is maybe not as efficient as how you would design a beam to column connection for a single-use stadium, but by putting a little bit more material and design thought into it, you allow for the disassembly of the structure. So this idea of rationalization and modularity is really important. You need to maybe do something slightly less efficient for a one-off to gain the benefits of deconstruction and reuse somewhere else. And there's obviously some friction here. You need to be confident that stadium is going to be reused to gain the benefits of that initial investment. And we'll come back to that later, I guess. Rationalizing your structure goes against some of what we think of when we say we should design highest utilization, efficient, clever structures with no extra fat in the system. Design for disassembly maybe needs that extra fat. The idea of having everything removable and stackable extended not just to the structural frame and the containers themselves, but also the bleachers and the concourse slabs. So there were some nice metallic solutions to this, which looked at replacing what might typically be precast concrete, single, double, triple Ls, and instead having these folded metal plates which bolt together and gain their stiffness from those connections. So these thin metal sheets can then be unbolted, stacked on top of each other, transported, reassembled. The concourse slabs have this orthotropic steel deck panels with only sort of 6 different sizes and designs, and these were used throughout the stadium. So you're working with a limited palette of spans and elements, but these are your components that you work with. So you have these sort of maybe higher energy use orthotropic steel deck systems instead of hollow core or concrete steel deck with concrete slabs. But they allow for that transportability and reuse, and they're much lighter, which has a big impact on the rest of your structural system. So how does that look together? This is one of the typical details of the stadium, and you see a lot of the things that we spoke about. So The first thing you see is that column to beam connector with different dimension beams interfacing in there. You see the single pin connections for the beams and columns. You see some diagonal plan bracing, which provides diaphragm stiffness to the concourse slabs, which you don't have in those orthotropic decks. You see the shipping container sitting on the system in yellow. You see some removable clamps that are fixing the orthotropic deck to the flanges of the beams. Those can be taken apart and reused in the next site. And you also see a QR code on the steel, which wasn't part of a really complicated material passporting system. This QR code is part of the steel fabrication process and their way of tracking it. But I think on future projects should be involved in a better tracking of where the elements move and what their roles were in the stadium. Because if you have your 3D digital model and you have your QR code for every element in it, you have a lot of information which has value for future reuse. So keeping those QR codes visible, unpainted, has some real value in the stadium for future use. Talk a little bit more about the difference between a single use or a double use stadium. So these are not real values that you see in this chart. These are indicative, but the point is to show sort of the key principle between a circular economy stadium designed for disassembly or a linear economy stadium, which is designed for a single use. So the bottom in orange is, say, the carbon dioxide emissions embodied carbon for building 2 stadia. So you have a stadium in Doha, and then you have another stadium at a separate location for the next World Cup. But say we had to build MetLife. We built the stadium 974, and then we said, oh, having a World Cup here, we need to build MetLife. You have 2 stadiums, all the emissions associated with those are in the atmosphere. The circular economy stadium, with its modularization and some of the decisions to transportability, if you look at just the first stadium, maybe has more carbon dioxide emissions. Using more steel, making some decisions which are not embodied carbon optimized for that first stadium. But if you then consider the emissions from disassembly, you have to use machinery to disassemble. The emissions from transport, the stadium has to go somewhere on a container ship, and the emissions from reassembly. Those are going to be less than building a second stadium. So if you're reusing the stadium at a second location, you then get that benefit, that delta 2 at the end. So it's an offset, it's a gamble. You invest in that first delta 1 of additional emissions to reap the benefits later of delta 2. This is the principle. And where we are at the moment is we're on stadium 1 still. So the client's still looking for a suitable site or reuse for the materials, but I think this is ongoing work still. So I'm hopeful that we'll get to that opportunity where we've offset the construction of the second stadium by using the first, and then we get to see the benefits of that. But we're not there yet. Okay, so we talked about these 5 projects, and I think there's some conclusions that we can draw which are helpful for us. So one is from deconstruction, we want to match element supply and design demand. That's a really important part. We don't want to store materials if we can't store them. We want to make sure that what we deconstruct and spend money doing has value. That was kind of one of the key outcomes. It really helps that the owner of the existing materials is also the potential owner of the new structures. So if there's a sort of closed ownership loop of the steel, like we also saw for the footbridge in Saint Denis, the owner can realize financial and time benefits, which it might be harder for other people to realize. The owner can own that risk in that to get that benefit. One of the key things is to include deconstruction and this concept of reuse early in the project. So that's maybe the answer for everything that we do, but it makes a really big difference on making sure the contractor and the client and everyone has thought about what they need to do differently for deconstruction and reuse. For the Lucie Briard footbridge in Saint Denis, the opportunities for better outputs, for better results were clear. So the opportunity to do an embodied carbon calculation and quantify some of the benefits of reuse can be quite powerful, particularly for a client like the municipalities for the Olympics. For Paris, they had really clear sustainability goals, which they needed to meet. So doing something like this and saying that this is what we think we've saved through reuse can be quite powerful. the Geisberg bus station was a really nice example of doing something quite simple, but having very clear specifications and incorporating it early. And that unlocked a lot of things. Early use, clear specifications of the client who wants it. Everyone figures out how to achieve it. For circulating matters, we had some challenges with determining those design values, and I think this is for steel. We have some confidence in the material that we're working with. For wood, for masonry, for concrete, there's less confidence for designers on what we should do for assigning design values. I think what's clear here is that we could do better on providing some information and guidance to fill that gap. So what can we do to provide designers information from previous work to say, this is how you design with reuse, this is the guidance that we would suggest. And then for Stadium 974, the whole team have to be on board, and then you can really realize a design which is quite different and benefits from that. But you also need to, if you're designing for disassembly, you need to be pretty confident that it will be disassembled. Otherwise, you're maybe not making a smart decision. So there's always some challenge there of what you can control. So here we are. Further reading. Some of these projects, there's a bit more information that you could read up on, and I guess I should particularly promote the one in the middle. So for the IABZ conference in Ghent this year, my colleague Apolline from the Paris office presented the steel reuse bridge in Saint-Denis at the conference, and that's in the proceedings, and that's good IABZ stuff that you should read. There's like 800 pages worth of stuff in there, and some other really good circular economy outcomes from the Netherlands included there. Some really interesting case studies from Amsterdam on bridge assessments and reuse for the hundreds of bridges in Amsterdam that go over the canals. And that's it. So take some questions, and always thanks for listening.
Thank you, Dan, and yeah.
You may have mentioned it, but I was just wondering for Stadium 974, who was the owner of the kind of structure after disassembly? Like, because the client purchases, I guess, the building, and then afterwards, would they then go back to you and sell it to someone else, or how's
So the client owned the stadium. Stadium is still in place, standing.
Okay.
So it's still in its format. And it's on the client to then for second use. So
Okay.
that's their risk and burden that they take.
But I guess then they would have to go back to say people who deserve it to get kind of that whole parts.
Oh, sure. I mean, I think that they probably would. The easiest route would be to go back to the same design team.
Yeah.
But the elements and the design are fairly clear, and you could anyone could go through and do the same thing again. But the loading is documented, the design criteria, the reports.
Cool. Thank you.
Yes, we can look at this online as well.
Yeah, I forgot about that. Actually, good.
If you have any questions online, you have to use the hand symbol.
Yeah, or actually, I'm checking the chat
Oh,
also. I posted there. Well, I have a question. What do you see in terms of requirements coming from the clients, particularly in the US, for using this principle?
Yeah, it's a really good question, and it comes to the heart of this decision. You really need client buy-in to do this. Someone has to own the risk and have the responsibility to change that. So the client is important, and I think Montreal is an interesting example where the client, it wasn't their idea, it was Stefan's idea actually. But we then presented to the client and said, "What can have you considered this? Would you be interested?" And a lot of these municipal clients, they have requirements to meet sustainability goals for the city or for the province in Canada. They're very receptive to this stuff. Examples from other parts of the US that not SPV projects, but the Boulder Community Hospital deconstruction and reuse in Colorado. The city of Boulder wanted to do it. They wanted to reuse that material on other projects in their city. So the municipality had their own motivation and goals, and they pushed that through. So that can be really helpful. The Saint-Denis Bridge, I think, is a nice example of the client being open to it for sustainability reasons, but really doing it for time and money reasons, which is maybe it was a slightly unusual place and time, but shows that the motivation doesn't always need to be sustainability focused. It can also be on securing material. You know you have the material, you know when it's going to be delivered because it's already there. It's already quite lucky. So client is really important. I don't know how many non-municipal clients in the US or Canada would be looking at this at the moment, but
We also looked at this project now in New York where they transformed the college or.
yeah, so there's a big project going on in New York City at the moment, which the Economic Development Corporation are the client for Spark project, which is the demolition of Hunter College on the east side of Manhattan, which is a really exciting one for the circular economy in New York City because people are looking at all of these materials and understanding what a deconstruction process looks like in New York City for some quite messy buildings and how to find people to use that and to get the benefits out of it. It's a really interesting project. It's a hard one because it's not it's a good example of how the value of the materials you build is really important for the future. So designing for disassembly with materials which can be taken apart is great. If you're working on a building which was built in the or sort of in the post-war period with like really quite crap brick, like no one wants it. No one wants that. Well, few people want that for reuse as it is. So the quality of the materials that we use has a big impact. So the older buildings, that's some really high quality stuff. We maybe have a period where some of the buildings and structures that we work with, we as designers at the time, we weren't using the highest quality materials, and that's going to bite us.
But when it comes to steel cables, for example, I imagine that there should be some testing done before they are reused. How extensive is that? And I mean, we're on brand new ground, right? It's not like there is a code that tells you how to test it. Or... This
is what keeps us busy at the moment. But I mean, there are two different approaches to this. Some steel cable is reused already. For there's kind of a thriving market of sort of the movable ropes from cranes and systems and docks. A lot of that gets donated to charities who build suspension bridges. Exactly. To Prosperity are using it. They're not doing any testing. They're assessing for visual damage in what they see. I think they're using a very hefty design factor. But those are quite small pedestrian bridges, and there seems to have been an understanding that that approach is suitable there and would be hard to apply here. So what we've been looking at is what sort of testing would we need to do and how would we do it for structural cables in North America, say, or other parts of the world. And there are some questions on how big a sample do you need to test? How do we get over doing sort of magnetic resonance testing for the cables? We destructively test some, and then we want to non-destructively test the rest. But there are some challenges there because all the non-destructive testing for cables is primarily based on the idea that you keep your equipment in one place and your cable moves through it. So this is for cable cars and things like that. So there are some systems that work on cable-stay bridges, which run up and down the cables, and that's maybe more appropriate for this. But this is, we think about it for maintenance and checking. We don't think about it for reuse. I think maybe what's been more interesting from our thoughts about this particular Montreal thing is that some of the challenges are economic, and you have to really, to make it viable to reuse cables, you probably need to use it with the sockets in place, because the sockets and the socketing is a really high cost component of the process. So if you cut the sockets off and you say, I've got this nice cable, I'm going to say, I need to put the sockets back on. That's like, 3/4 of the cost. You idiot, what have you done? So that's a challenge, because then you're designing with quite specific cable lengths and specific sockets. And so for structural steel, I think the industry is really robust, particularly in the UK and in Europe, and working on it here in the US. For structural cable, this is sort of, we're working on this new ground for static cables that we're working on at the moment. For wood, there's some existing knowledge base in comfort, but less defined than steel. Concrete is still earlier days, and there's some nice examples in Switzerland and the UK at the moment of concrete reuse in cutting and testing, but we're structural steel is your sort of low-hanging fruit for this. Woods within context can be really viable. Steel cables, concrete. We'll come back next year and we'll have more information.
The other question? One who's really already asked questions, but I'll ask you one more. I think the challenge is really to find who needs what where, right? And I think I started reading something about an effort to create a database. Is there anything?
Yeah.
real?
Yeah, look, it's a hard one, and part of the problem is that it's really regional. But there's no sense in us deconstructing something here and then sending it to California. It's not smart. So what you need to have is sort of a selection of local ways of sharing that information. And there's movement in New York City to do something like that at the moment. There's one in the sort of beta phase right now for sharing material. Some of the New York City departments have internal tools that they use for this sort of stuff. There are things like Reaply, which is primarily for non-structural elements at the moment.
What is it?
Reaply, RHEAPLY. It's an online platform for usually things like office chairs, things, and they're considering trying to get into the structural material market. The problem with some of this is we still have certification and testing barriers, which we haven't fully resolved. So it's hard to do it in quite the same way as in structural stuff. But there are in London, there are some companies who have really taken a lot of this stuff. They do the deconstruction assessments, and then they receive the material, and then they sell it before it's out of the building. And they've got quite smart platforms that push it around, and they have a network which they contact. And if we could do something similar to that, but for structural materials, and if we could do it not only in one city but in multiple cities, then I think there's an opportunity. But it's hard to get the infrastructure there, and some of the challenges, certification are currently a bit of a problem.
All right, anybody online, any questions? I don't see hand raised hands and nothing in the chat.
Thank you very much.
All right, well, thank you all. I wanted to thank Howie for offering the space and SPP, of course, in general, for supporting this presentation. Congratulations on that idea. Something. And yeah, as I said, November 18th, we have the next event. I hope that's online only. I hope to see many of you and bring your friends. We do have some flyers here, so I'll put them on that table. So on the way out, if you want to, something about IAPSIs. And whoever wanted that PDH has signed the forms for hopefully. Okay. You need more. Wait, I don't know whose pen this is. Yeah. Okay, well, thank you, everybody. Thanks, have a great evening.
Oh. Nice to meet you. See you around.
Nice to meet you.
Yes, I am the meeting door.
Yeah, how is for you?
Yeah. Yeah.
You get more.
But it.
Yeah, first recorded.
Yeah.
I think you can just close it.
Oh, wait.
That we-
I don't see.